Okay, so let's do a first example. Let's say we want to find the integral from -2 to 5 of 6 dx. And we're going to do all of these using the fundamental theorem of calculus. Okay. So, step 1. Find the antiderivative. Okay, so here remember the dx is part of the integral notation. It represents the infinitely thin rectangle width. And so you always have to have the dx in there. Okay, so we're going to find the antiderivative of 6. What's the antiderivative of 6? Well, that's just 6x, right? So here, this is where you want to keep those all your antiderivative rules handy, and just until you memorize them. But basically, remember that if you find the derivative of 6x, you would get 6, and that's exactly what you want. Okay, so then what you do is you're going to plug in, once you find the antiderivative, you're going to plug in the end point minus the beginning point, or since we're looking at it in this form, we're going to say we're going to plug in top and then minus the bottom. So the notation is you put a vertical line and then you put the numbers just like you see them here, -2 and 5, and then you plug in the top, so that would give you 6 times 5, and then minus, you're going to plug in the bottom. So that's going to be 6 times -2. And so you find out what that is. So that's just 30, and then plus 12. So this is equal to 42. Now this function, you could have also done by drawing a picture, right? So let me just do that real quick, since this is such an easy one to do. You have the function 6, which is just a horizontal line. And if you're finding the area from -2 to 5, that's just the shape of that is just a rectangle. The width is 7. The height is 6. And so when you find the area of that, the area is equal to 42, which is exactly what we got with our fundamental theorem of calculus. So that was just a fun one to show you. Okay, now let's do another one. Let's say we have the integral from 0 to 1. Now we're just moving along here from easy to more difficult. So let's say we have the integral from 0 to 1 of x. There's also another one we can do graphically, but let's do it using the fundamental theorem of calculus. Okay, so again, step 1, find the antiderivative, which is, using the backwards power rule, x squared over 2. And then we're going to evaluate from 0 to 1. Okay, so then we plug in the top, which is 1. So we would have 1 squared over 2, minus, plug in the bottom, which is 0, 0 squared over 2. And so then we just get 1/2. That's it. It's easy, right? Easy, easy, easy. The fundamental theorem of calculus just simplifies this so much. Let's do another one. Let's say we want the integral from 2 to 4 of x squared dx. Remember how much trouble we had with this one with finding the area underneath the curve of this using Riemann sums? It was nuts. It was bananas. But using the fundamental theorem of calculus, it's 2 steps. Find the antiderivative. Boom. Backwards power rule. X cubed over 3. Evaluated from 2 to 4. Done. Then plug in. So I've got 4, plug in the top, which is 4 cubed over 3, minus plug in the bottom, which is 2 cubed over 3. Okay, 4 cubed is 64 over 3, minus 2 cubed is 8 over 3. And so this is simply equal to... Okay, so we continue with more examples, lots and lots of examples. Let's say we want to find the area underneath the curve from pi to 3 pi over 4 of cosine of theta d theta. Okay, So let's say we've got, I want to draw the picture for you, what this one looks like. So let's take a look at this one. So, I mean, this is great, this fundamental theorem of calculus business. We've got the cosine of theta, which looks like this, right? Just rough sketch, of course. And so let me plot the points here. So this would be where 2 pi is, and this is where pi would be. And then over here would be 3 pi over 4, right? Which is a little bit less. Now notice that these are not going from smaller to bigger. This is, you know, the area underneath the curve, right? But it's going from a bigger number to a smaller number. Now, from the properties of integrals, you know, you might be thinking, oh, well, we have to flip it because it has to go from from smaller to bigger, and then you have to, you know, do the negative sign on the outside and all that stuff. But see, it's all built into the fundamental theorem of calculus. You don't have to worry about anything, nothing. So all you need to do is you find the antiderivative, which is sine of theta, and you're going to evaluate from pi to 3 pi over 4. Okay, so then you plug in the top. So you go, okay, so let's plug in the top. So sine of 3 pi over 4 minus, plug in the bottom, sine of pi, and this is equal to sine of 3 pi over 4, that's root 2 over 2, and then minus sine of pi, that's 0. So this is just simply equal to root 2 over 2. Now you might be thinking, well, wait, hold on a second. It's positive, but it's underneath the curve, so shouldn't it be negative area? Okay, so I'll let you guys think about that one. Did we make a mistake, or is there something else going on? Okay, I'll tell you. So remember the property that says that you can flip the limits of integration as long as you change the sign on the outside. So this integral is equal to the integral from 3 pi over 4 to pi, but taking the negative there on the outside. And so notice that when you find this one right here, this integral would be negative, but then when you multiply it times this negative on the outside, then it becomes positive. So that's why it's positive, but the great thing is that it's all built into the fundamental theorem of calculus. You don't have to worry about it at all. So what happened was the area is underneath the x-axis, so it is negative, but then because the limits of integration are flipped, you got, in a sense, a double negative, and so it turned that into a positive value. Just wonderful. Absolutely wonderful. Okay, let's do another one. Let's say we have the integral from, let's say, how about e to e squared of 1 over x dx.